My name is Gary Mitchell, and I represent the spray paint booth pressure control system. My other teammates are Bradley Turner, Troy Talent, and Daniel Stalker. Brief outline of what we'll be talking about. Be doing the system background. Within that system background, there's going to be a description, SSOC results, step function results, frequency response, relay feedback, the root locus theory, the root locus plot, and then we'll get into the proportional feedback controllers and the proportional interval controller with results and conclusions. Tim?
Yeah, you're going to need to skip about 30.
Looks hard work for nothing. That's how it rolls. I wanted to talk about this stuff. Yeah.
Other side. That little dot. Right. Yeah. No.
You want this one here? Okay. This was for the proportional controller. We had the different KC values that we, I believe this is the experiment. So these are the actual KC values we found for each decay. The first one being critical decay, and for pressure from 1 to 4 centimeters H2O, Brad found that the KC for critical decay was 17 for 1/500th decay, 25, 1/10, 35, 1/40, 50, and for ultimate decay 70. And we also found the settlement time for each of these, and then the offset. And this is for each group. And they also ended up being completely different from what we got for our root locus. This is the same stuff for 7 to 10 and 10 to 13. I have the graph next that actually compares all this together. For the root locus results for KC, this was in Brad's area. The KCD actually ended up being really close to what we had predicted with the root locus, but as we go up in the decay, it gets a lot. The experimental KC is a lot lower than what the root locus predicted. That remains true for the majority of everything we did. Daniels actually ended up getting the KCU the same, but that may be because if you keep going higher than the KCU, it's going to still be critical. May not have been exactly where it became critical. Or, you know, thank you, Brad. You're the man. For 7 to 10, the same happens here. The actual KC is a lot lower than the root locus, and the same with 10 through 13. Next, for the proportional interval control, we did root locus as well. But for the root locus, we took the T-naught that we used. In this case, it was the T-naught that we got from the sine response that Troy did. You take the T-naught, multiply by 3.33, and you get the tau sub I. And these are the results for the KCUs for each of the decays. For critical decay, we got 1% per centimeter H2O, 2.9% percent per centimeter H2O. For 1/10, it was 7. For quarter decay, it was 9.4. For ultimate decay, it was 14. And the FU was 30. Then we took that tau I that we found in the previous one, and we did one greater than that. And actually, this was less, I believe. No, it's more. Did one greater than that, and found all the decays for it, which ended up being 9.6, 16, 31, 41, and 62. And then we took one less than the tau sub I that we did in the first one, and found the KCs for it, which ended up being really, really, really low number. Most likely it was 0, but we put 0.00001. 0.29, 0.74, 1.8, and 14. This is a comparison of the KCs that we got with each tau sub I. If you look at the graph, you'll notice that the red on each one of them, which is higher than all the rest of them, that's because the tau sub I is greater for the middle one than it is for the other ones. The other ones are lower, so the KC is going to be greater for that particular tau sub I for each of them, as well as the ultimate frequency. This is for, it remains true for 4 through 7 centimeters H2O, where the middle one, which is the highest, ends up being the greatest KC values, as well as for 7 through 10 remains true, and for 10 through 13, which this is so much greater because the difference between these tau sub I's are so much, they're a lot greater than the other ones. For the PI experiment, the proportional interval experiments, there were two important things that we wanted to look at. The settling time and whether or not it was monotonic or oscillatory. And then there were a couple drawbacks from the PI, which are the reset wind up and reset wind down. And then this is the open loop transfer function for a PI controller. Whenever we did our experiments, we wanted to look at, as I said, the settling time. The settling time is how long it takes for the output to reach the set point, the change in set point, whenever the set point changes. So in this, the settling time ends up being about 10 seconds. If it's oscillatory, it continues to, or it'll start out as almost sine wave-like, and then sometimes it has decay and sometimes it doesn't. Monotonic is essentially a constant line that's eventually ends up being a straight line across the set point for the PI controller. This is an example of reset wind up. Whenever the set point changes, the input actually goes all the way to 100 and stays at 100 for some time, and then it readjusts itself and makes it so the output reaches the set, actually goes down to the set point as desired, although it didn't happen necessarily the way that we wanted it to. Reset wind down, it's a lot like reset wind up, except instead of going to 100%, it goes down to 0% and stays at 0% for some time, and then it goes back up to the output goes back up to the set point. What?
It went down to 0 to the set point.
This is an example of Troy's experiments. We tried the different tau I's and KCs that were found in the root locus, and for tau I equals 3 and KC equals 16, whenever the set point changes, we found a settling time of 5 seconds. The predicted decay ratio was 1/500, and Troy said the actual decay ratio was 1/500. For tau I equals 3 and KC equals 9.6, we found a settling time of 5 seconds, and the decay ratio was critical decay, as predicted. For tau I equals 0.7 and Kc equals 2.9, we found that the settling time was 10 seconds, and the predicted decay ratio and actual decay ratio were both 1 to 500. For 0.7, a tau I equals 0.7 and a Kc equals 1, the settling time was 10 seconds, and the predicted decay ratio and actual decay ratio were both critical decay. For 0.2 and 0.15, the settling time was 20 seconds. The predicted decay ratio was critical, and the actual was critical as well. For 0.2 and 0.2, the settling time was 10 seconds. The predicted decay ratio was 1 over 500, which the actual decay ratio was 1 over 500. After taking all the settling times that we did experimentally and put them together, for 1 through 4 centimeters, the lowest settling time was Kc equals 2 and tau I equals 0.7. This actually ended up being the recommendation for the entire system because the Kc was lower than any of the other ones that had a low settling time. And the minimum settling time over all of them was 5 seconds. So that's why I went with that for the entire system. For 4 through 7 centimeters H2O, the suggested for this region was Kc equals 10 and tau I equals 1.3. We picked that for this region because the settling time was the least and it was monotonic. For 7 through 10, the suggested was Kc equals 12 and tau I equals 2. The reason it was suggested is because it had low settling time and it was monotonic. For 10 through 13, it was Kc equals 10, tau I equals 3, because it was the reason we didn't pick Kc equals 16 and tau I equals 3 because the K equals 16 was oscillatory and the other was not. This is a graph of the one that I said was recommended for the entire system. I tried to do the biggest jump that you could possibly do for this system and to see how it would react. Unfortunately, it did have some wind up, but it still settled within 10 seconds to what the customer desired. So essentially, the maximum settling time was 10 seconds. In conclusion, the proportional root locus did not match the data. The PI root locus did match the experimental data. The problem with proportional controls was offset, and that's not desired at all. And then the problem with proportional interval controllers was that it had wind up and wind down, but over time it still ended up having the right set point. The recommended parameters for this system were Kc equals 2% per centimeter H2O and the tau I equals 0.7 seconds. And with these parameters, wind-up only occurs whenever you're trying to go from 1 to 12 centimeters H2O. And the max settling time is 10 seconds.